Hello, art students. Today, I'm going to show you how to calculate backpropagation in neural networks. We'll use the same example as we did in the last video on forward propagation. So if you haven't watched it, please refer to it. In the previous video, we calculated the total error, E total, to be 0.024. The goal of backpropagation is to make this error even smaller and eventually minimize it by adjusting the weights of the network. So your neural network learns from its mistakes and gets better over time through backpropagation. Our goal in backpropagation is to update these weights W1 through W8 in order to minimize the total error, E total. Our process of backpropagation will have two steps. We have two steps in our example because we have one hidden layer. The first step updates its weights between the hidden layer and the output layer. So for Z3 and O1, we update W5 and W6. And for Z4 and O2, we update W7 and W8. And the second step updates the weights between the input layer and the hidden layer. So for Z1 and H1, we update W1 and W2. And for Z2 and H2, we update W3 and W4. If we have more hidden layers, there will be additional steps for each hidden layer. We use chain rule from calculus to calculate the gradients of E total and with respect to each weight, and then adjust the weights to minimize the error. In backpropagation step 1, we need to update weights W5, W6, W7, and W8. This process is the same for each weight, so let's start with updating W5. To update W5, we need to calculate the partial derivative of E total, which was 0.024 from the previous video. Using the chain rule, we can break this down into three parts. E total respect to O1, O1 respect to Z3, Z3 respect to W5. We already have the value of E total, and the formula for E total is 1 over 2 multiplied by the difference between predicted O1 and the actual O1 squared plus 1 over 2 multiplied by the predicted O2 and the actual O2 squared. Now we calculate the partial derivative of E total with respect to O1, which is minus the actual value of O1 and the predicted value of O1, which is minus 0.4 minus 0.609. Now we calculate the partial derivative of O1 respect to Z3. Now remember, O1 was the sigmoid function, which was our activation function. Sigmoid function, remember the formula was 1 over 1 plus e to the negative x. Now the derivative of sigmoid function is the sigmoid function itself multiplied by 1 minus sigmoid function. So for this, we can just say that the partial derivative of O1 respect to Z3 is O1 multiplied by 1 minus O1, which is 0.609 multiplied by 1 minus 0.609, which is 0.238. Finally, we calculate the partial derivative of Z3 with respect to W5. And note that this is just H1. So we can calculate it as 0.52. So multiplying all these together, we get 0.209 multiplied by 0.238 multiplied by 0.52, we get 0.0259. Now we can update W5 with gradient descent formula, which is updated W5 equals old weight minus alpha. This is the learning rate. Let's say our learning rate is 0.5 for now, multiplied by the partial derivative of E total with respect to W5, which is 0.45 minus 0.5 multiplied by 0.0259, which is 0.4370. These are the updated weights of W6, W7, and W8. Please calculate them on your own and compare with these answers.